And then you've got this, the infamous z equal tangent of x over 2 substitution. So if you have a rational function, and the rules we talked about in 3.2, they don't really apply here. Okay, if you do the z equal tangent of x over 2 substitution, and you go through and calculate what's going on here. So if z equals the tangent of x over 2, and we restrict x, then you can get x over 2 is the inverse tangent of z. So x is 2 times the inverse tangent of z. So if we look at x between 0 and pi, or excuse me, if x is between negative pi and pi, we let z equal tangent of x over 2. That's equivalent to x being 2 inverse tangent of z. And so the dx is going to be 2 over the derivative here, z squared plus 1. And then if you use this along with some other identities from trig, so that's where the dx comes from. The cosine and the sine, these are standard half angle stuff from trigonometry. You can take a function like this and turn it into a rational function that we can use partial fractions or other techniques on. So we take a rational function in terms of sines and cosines and turn it into a rational function in terms of z's. So let's just walk through this example. We get the integral of 1 over 4 minus 3 cosine theta d theta. We're going to let z be the tangent of theta over 2. And so we're going to plug in d theta is 2 over z squared plus 1 dz. And notice the way I try to distinguish my 2's here from the z's is I put a line through the z. And the other formula we need is the cosine. So the cosine is 1 minus z squared over 1 plus z squared. And once again, this is a half angle identity from trigonometry. So if I stuff all this in to the integral I have, 4 minus 3 times 1 minus z squared over 1 plus z squared times d theta. We would get to this. So we're taking a rational function involving cosine and turning it into a rational function in terms of z. And the idea is by doing that, the worst case scenario is we'd have to run it through partial fractions. So let's take this and do the algebra on it. So we're going to have 2 in the numerator here. I'm going to multiply the z squared plus 1. It's got to get multiplied by both of these terms. When I multiply by the first term, we're going to be multiplying z squared plus 1 times that 4. When we multiply through the second one, it'll cancel the denominator here. And I'm left with minus 3 times 1 minus z squared dz. So we're taking this, distributing it to both. Here it'll cancel that out. I go through the arithmetic here, the algebra here rather. I got a 4z squared plus a 4 minus a 3 plus a 3z squared. So I'd have 7z squared altogether down there, plus 1. And I can take the 2 out and take the 7 out. I'll be left with 1 over z squared plus a 7th dz. And this is an inverse tangent form. So I can write that 1/7 as 1 over root 7 all squared. And so I can use the inverse tangent formula here. So this is going to be 2/7 times 1 over root 7 times the inverse tangent of z over 1 over root 7 plus c. And remember that 1 over, doing the fraction gymnastics, we're just going to have 2 root 7 on the top. Inverse tangent of z times root 7. And now we plug back in. Z was the tangent of theta over 2. So we get 2 root 7 over 7. Inverse tangent of root 7 tangent of theta over 2 plus c.